Non-linear decision boundaries. So far, logistic regression draws straight lines or flat planes in higher dimensions. But what if the data is not linearly separable? What if the boundary between classes is curved? In this video, we learn how to make logistic regression handle non-linear boundaries. The trick is surprisingly simple. Imagine data points in 2 dimensions. Feature x1 and feature x2. Class 1 points form a cluster in the center, near the origin. Class 0 points surround them in a ring. The true boundary is a circle. Points inside the circle are class 1. Points outside are class 0. This is a common pattern in real data. Think of normal versus anomalous readings from a sensor. Or healthy versus unhealthy patients based on 2 lab values. The boundary is clearly circular, not a straight line. Let us try standard logistic regression on this data. With features x1 and x2, the decision boundary is theta 0 plus theta 1x1 plus theta 2x2 equals 0. This is a straight line. No matter what theta values we learn, the line cannot curve. It will cut through the data, misclassifying many points. On one side, it catches some class 1 points, but it also includes many class 0 points. The training accuracy is poor, maybe 60%. The model simply does not have the capacity to represent a circular boundary. A straight line cannot approximate a circle. We need more expressive features. Here is the key idea. We add polynomial features. And instead of just x1 and x2, we also include x1 squared, x2 squared, and x1 times x2. Our feature vector goes from 2 dimensions to 5 dimensions. Now the decision boundary equation is theta 0 plus theta 1x1 plus theta 2, x2 plus theta 3 x1 squared plus theta 4 x2 squared plus theta 5 x1 x2 equals 0. This is the equation of a conic section. It can represent circles, ellipses, and hyperbolas. We are still doing logistic regression. The model is still linear in the parameters theta. But by transforming the input features, the boundary in the original x1, x2 space can be curved. This is exactly the same idea as basis expansion from linear regression. We engineered new features. The model itself did not change. Let us train logistic regression with these polynomial features on our circular data. The model learns theta 3 and theta 4 to be roughly equal and positive. The boundary becomes approximately x1 squared plus x2 squared equals some constant. That is a circle. Exactly what we needed. The accuracy jumps to nearly 100%. And we can go further. Add cubic features, quartic features. The boundary can become even more complex, but be careful. More features means more risk of overfitting. A model with too many polynomial features will memorize the training data and fail on new data. We will see how regularization helps with this shortly. The principle is general. If you suspect a non-linear boundary, engineer appropriate features. Domain knowledge helps here. If you know the boundary might be circular, add squared terms. Let us recap. Standard logistic regression gives linear decision boundaries. For nonlinear patterns, we add polynomial or transform features. The model stays linear in parameters, but the boundary curves in the original feature space. This is the same basis expansion idea from linear regression. More features give more flexibility, but also more risk of overfitting. Choose your features wisely using domain knowledge when possible.